All right, welcome everyone. This is the F110th Autonomous Racing Competition. This is the 22nd international competition that we are hosting, the 9th one this year, and this has been a very exciting year. So today's competition is actually the virtual competition that we're going to talk about. And later this week, we'll have the physical competition right around the corner that we are also hosting. So the agenda for today is for the first, 10, 15 minutes. Professor 𝗥𝗰𝗶𝗴𝗂𝗲 from Clemson University and myself, Rahul Mangharam from University of Pennsylvania, will give a broad overview of F110th, and then we'll pass it on to the hosts of the virtual competition to describe what the competition was about. There were over 54+ teams in this year's competition, and they'll go through the process, and we'll also hear from the winners of the competition. And then in the end, we'll just end with a few question and answer session and a discussion. So we'll wrap this up within the hour. So once again, welcome to F110th. So F110th is a community for autonomous racing of different vehicle scales, and these are engaged through courses that are in over and competitions. So the F110th is used by over 90 universities worldwide. And as I mentioned, we had over 22 competitions since the last few years. So the first question is really, why racing, right? So what is so exciting about racing? People have been looking at autonomous vehicles, but in autonomous vehicles, we're just optimizing for safety. And if you reach home like 3 or 4 minutes late, there's no big deal. You're not optimizing for performance. But in racing, you have this very tight tension between safety and performance. And if you're driving a little too conservative, you get penalized. If you're driving too aggressive, you crash and you get penalized. In fact, in Formula One racing, if you're just half a second too slow in your lap time, you're going to be out of the top 10. So that's a career decision. If you drive too aggressively, you get penalized, you crash. So here, the other aspect is that these vehicles are driving at their physical limits, at the limits of their tires, of their engines. And if you are not pushing your vehicle to the limit, then you are basically not, your opponent is going to, and they are going to outcompete you. And so this brings in the aspect of the full dynamics and the full physics that are required in this kind of competition. So it's a multi-agent competition, but with full dynamics involved. So fast speeds, fast acceleration, and very very quick maneuvers have to be made. So the virtual racing team for this year is hosted by Chinmay Samak and Tanmay Samak and their advisor, Professor 𝗥𝗰𝗶𝗴𝗂𝗲 from Clemson University. They built the simulators and the entire online system for the students to participate in these races. And they've shown in the last 2 races with over 57 teams in the previous IROS race, and then over 54 teams in this race over here at CDC. So over 100 teams have competed in these competitions, and they've shown that this kind of system is very scalable, and it captures the full dynamics of the vehicles, allows for reinforcement learning, allows for SLAM, for sampling-based planners, for MPC, all the full stack, right? So joined also with us is Johannes Betz, who's a professor from TU Munich, and he has been one of the key people in building up F110th worldwide. Later this week, on Wednesday and Thursday, we will also have the physical race, and that team is hosted by the students and faculty from Unimore. And there's a great race that you will see down the corridor, and I welcome you to join us there. So the reason we started F110th is that because to build an autonomous system is very complex, and it requires many different skill sets. And usually students learn one thing at a time, and they assume everything else is idealized. And so this was to bring in a complex enough system, but not too complex, and to introduce them to perception, planning, control, and the full autonomy stack, and they get to build, drive, and race these vehicles. So here you can see the vehicle is like an RC car, but it has an onboard GPU. It has 2D LiDARs. It has depth sensors, an IMU, and many other aspects on board. But it is not too complex. And the entire system is supported by a lot of system software. And the best part is that students get to actually build these vehicles, drive them, race them, crash them, and learn from them. And so we say that they are 1/10 the size, but they're 10x the fun. And so this platform is also supported by really good simulators. There are physics-based OpenAI Gym interfaced simulators for control and planning. And then for perception, planning, and control, you can see these kind of visualized simulators with these vehicles involved over here. And they have high fidelity vehicle models and that are optimized for this. So as I mentioned, there are over 89 to 90 different worldwide partners and universities that use these vehicles for their research, teach this as a course, and compete in these competitions. And it's a very vibrant community with a lot of engagement online. And this year, we've had 9 international competitions in 2024 alone at top robotics conferences like 𝗥𝗏, IROS, at Cyber Physical Systems Week, and then at transportation conferences such as Intelligent Vehicles, and also several competitions worldwide, right? So from Japan to Hong Kong to South Korea to Canada to Abu Dhabi, and now this time in Milan. And next year, we will again have several different competitions, but this is just to show you that this is a community that spans robotics, controls, and transportation. And so this is an example of the competition that was held earlier this year in Jeju and Korea as part of the IEEE Intelligent Vehicles competition, and there were over 35 teams involved in that, and over 300 students participating in that competition. And this was the first of the 2 competitions held in Korea. And it's just to give you an example of what a physical race looks like here. And then there were many other competitions. This was at 𝗥𝗏 in Yokohama, and you can see the vehicles are driving at full speed, drifting down the corridors. And then many engagements worldwide, with different university communities who have boot camps, who have tutorial sessions that are prepping up their teams in regional competitions. And our goal with F1TENTH is to help the community build, code, and race these systems. And this is basically to take them from simple gap finding algorithms to run SLAM. SLAM has been running for many years very efficiently on these platforms, from simple obstacle avoidance systems to running sampling-based planners like RRT, RRT star, and many other neural operator-based algorithms that run on these platforms. From running simple PID control to running MPC. MPC is a standard part of the platform, MPPI, learning-based MPC, learning-based MPPI. All of these different control-based and tracking algorithms are standard in the platform. We also developed a course. This is an example of a course module. It assumes the students just have linear systems as an introduction, as a prerequisite, and then it takes them through building on ROS, building through the basics, and within 6 weeks, 6 lectures, they're ready for the first race. There are no exams, no midterms in this course. There are just races. Race 1 is just getting your car working with reactive-based planning. Race 2, they learn how to localize, they learn how to use SLAM, and then and build in pure pursuit planners. And then the cars run much faster, more confidently. And then race 3, they have all learning-enabled perception, planning, control on their stack with sampling-based planners, MPC, and so on, right? And then they basically are now in a much more sophisticated regime of racing. Towards the end of the semester, we have many different projects that the students choose from, or they design their own projects. And this is just an example of some of the projects that the students have done over the past semester. Yeah, I think someone is online. You just need to mute. So the Robo Racer is the new form of F1TENTH, because now we are expanding from just 1/10 scale platforms, and this is the website. Here you can go and find everything. How do you build the car? How do you start coding? And then how do you start racing?
If you want to change the setup of the car, it's because maybe your team is putting the components up and they figure out that this will work a little better. Is that allowed or not?
Yeah, good question. So what if you want to change something in the platform? So if you go for every race, we have a common set of rules, and the rules are quite relaxed. The whole point is we don't want you to spend more than this average platform. So we are not going to let you have more powerful motors, but there's a lot of freedom to have different tires, different types of chassis or compute platforms, or even a slight changes in mechanical designs. The whole point of this is that there is, like Formula One racing, that is a standard set of rules and a standard design that all teams have to follow, so that it then becomes a battle of algorithms. We don't want teams to compete based on their budget, but really this is an algorithmic competition. But there is a lot of freedom in that design, what sensors you want to use, because at the end of the day, the bottleneck is none of that. The bottleneck is not the compute, it's not the sensors, it's really putting together the whole autonomous vehicle stack. And that's what we've seen with teams. So great question. And so these are sort of how we started with competitions in Korea, Portugal. We had it in Torino in Italy back in 2018, and so on. And then in the past year, we've had many of these competitions worldwide. And they've been also hosted by many of the community members. Like in Italy over here, we have the Unimore team that has helped host and set up the whole race over here. And that's what makes it a very vibrant community. This is an example of the competition that we had in Philadelphia in 2022, just after COVID. It was one of the first times people got back to conferences, and you can see how happy they are after this, right? And they all have basically the standard vehicle design based on the very simple IKEA-like instructions that once you have the parts in 1.5 hours, you can build the whole vehicle, program it, and get it ready to roll. And this is an example of the race that we had in Philadelphia. And here you can see, I think this is ETH Zurich in the lead, and followed by the Penn vehicle, and they're trying to outmaneuver them. And I just showed you the clip of where they do the overtake for the winning lap. So all teams, when they come to the track, they basically build a map of the track, as you can see on the laptop here, and then they based on that map, then they formulate what is their race line, and then they formulate also what are their overtaking strategies, and that allows them to now figure out, okay, how do they navigate over here, and those are the kind of algorithms that then they would want to build in as they go through. So later this week on Tuesday, we have the practice day for the teams, then time trials on Wednesday, and then Thursday will be the race day for the in-person race. And this is kind of examples of the in-person races that we've had in the last 2-3 years. This was in 𝗥𝗏 in London, and this is an example of the IROS race that was in Detroit earlier this year. You can see how fast the vehicles, I'll play that back once again, how fast the vehicles are navigating between each other to do agile overtakes. Looks like Zoom is a little slow here, but and then this is what's happening under the hood, right? So you might say, oh, well, this is just little like a little toy system over here. Everything is fully analyzed, right? In terms of what is their grip budget, how much more can they accelerate, how fast can they make this turn. So students get an idea of the full dynamics of the vehicle. They get an idea of how perception, planning, control, localization all come together over here, right? So, and then they have this kind of dashboard that is behind the scenes. And so then they can optimize how they want to race as they go through that. There's also really good community support in terms of students building their own tutorial videos. And here you can see this has over 600,000 views for students explaining how they got started with F1TENTH. And then to complement all the the competitions, we have an education and a research agenda, and where we have many different types of workshops. So this is a workshop that we had in 𝗥𝗏 22 on challenges with autonomous racing, and brought a lot of the industry folks, a lot of the academic experts who are working on very nonlinear control, understanding vehicle dynamics, but in an autonomous setting, really pushing these systems to the extremes. And then there is a very theoretical side of F110th, which has nothing to do with systems really, and it is looking at multi-agent dynamic games. And this brings together all the folks in, from control theory to game theory, and which is really bridging, continuous time, games over here with full dynamics. And so we had several speakers here. I think this workshop was had over 90 people attended, and then this was a second workshop that we had in 𝗥𝗏𝗏, and that was also very popular, and brings together basically the theoretical side of speakers, right? So this is just to summarize, what F110th does is that through competitions, we really develop a very open source, fast and fun environment, right? And this is all supported by tutorials, lectures, platforms, codes, simulators. And there's a lot of research that gets done with F110th platforms. In fact, there are over 50 tier 1 published papers based on F1, whether it is generated data. Earlier today, we had a paper on conformal prediction for multi-agent games that also used F110th, for example. And there are several master's thesis and PhD thesis written that build and develop on top of F110th. So before we switch to the award ceremony for the virtual race, this is a schedule for the physical race that will be here at CDC. I welcome you all to come and attend here. And I'll now pass it over to Chinmay Samak and Tanmay Samak, who will also talk to us about the virtual race. And Professor Venkat Krovi, if you would like to give a few words from your side. Thank you.
Yeah, thank you, Rahul. That was a great overview of the movement, the F110 movement that you initiated, that has caught the imagination of the world, literally. Even as we were participating in this effort over now about 2017 onwards, almost 7 years, one of the biggest challenges that comes up in something like this is this requirement for being able to treat the system in an end-to-end setting, and to be able to evaluate different choices, the variability and the choices in potentially ahead of time in simulation before you're able to transition it to an actual system. So Chinmay Samak and Tanmay Samak, who will be speaking next, will give you a little bit of a perspective on how they evolved the AutoDRIVE ecosystem to now support this activity, and then successfully deployed it at IROS this year. And the second deployment now is at 𝗥𝗏𝗏. So Chinmay, Tanmay, please take it away.
Thanks, Dr. Mangharam and Dr. Krovi. So let's get started with some of the insights that we had from this competition and this bringing together of AutoDRIVE ecosystem with F110th. So first of all, we'd like to give a huge shout out to all the organizers, without which, like, it's these people that you see on the slide, and not just Tanmay and me, who made this competition along with the physical F110th race that you, like, some of you will participate in possible. And just wanted to acknowledge everyone's effort here. With that, let's talk about the F110th. I know Dr. Mangharam did a pretty good job already describing the F110th, so we won't belabor the same thing again and again. But as a key takeaway of what F110th is it is a platform that you see on the slide here. It is a RC car with autonomy enabled, so that you can do education for both undergrad and graduate level. You can do research, and most importantly, you can have fun doing both of them by racing autonomously. what we will see hereafter in the slide, especially from the digital twin of the F110th perspective, is AutoDRIVE ecosystem, wherein the idea or the ideology behind AutoDRIVE was to create a unified framework for designing, validating, and deploying autonomous systems through a concurrent framework where you can, for example, use the dev kit to prototype and develop your algorithms through different APIs and frameworks and interface them with the simulator to now verify them, put them through different corner cases, have them simulated across different variations of both the vehicles as well as the environment parameters, and have them tested rigorously before you now have confidence of deploying them in the real world, and then use the same pipeline to now actually transition them seamlessly from simulation to reality and then validate in the real world. What Dr. Krovi alluded to was AutoDRIVE started with just a simple 1/14 scale vehicle that you see in the top left of the slide called 𝗟𝗲𝗃𝗲. It's a completely open source vehicle, just like the F110th, where the chassis and all of the other components and instructions are made available. But after coming for our PhD at CUI-CAR, what we got the opportunity of doing is expanding AutoDRIVE across different scales and operational design domains of vehicles as well as environments. And that's what you see on the slide here, where we now have another small scale vehicle, the F110th, as well as mid and full scale vehicles targeting different ODDs for both on-road and off-road driving. At the same time, you also have representative scenes and scenarios for these different scales and operational design domains that you can now start developing and using to validate your autonomy algorithms. On the right extreme part of the slide, what you see is also a human-machine interface framework where autonomy is one aspect, but human-in-the-loop research is another. And combining the two is a very exciting part where you can start using teleoperation data or human feedback while online learning, or those kinds of ideologies to bring and immerse humans within autonomous systems. So what we'll be discussing today is the amalgamation of these two powerful ecosystems, that is AutoDRIVE and F110, to unlock the circle of opportunities that you see depicted on the slide, where both of them are open source and have largely community-driven and community-engaged efforts. We have got different aspects of both the platforms complementing each other and supporting each other through different aspects like dataset curation, for example, or research and educational resources, having high-fidelity simulation tools, development frameworks, as well as the hardware test beds. And most importantly, the excitement of competitions and international communities coming together to work on the same problem of autonomy is what is happening with both of these now coming together. So what you will be seeing in most of the slides today is the digital twin of the F110th in AutoDRIVE. And this is just a sample video that we created, I think about a year ago, if I'm not wrong, when we first created the F110 digital twin within AutoDRIVE simulator. And this just shows the kind of capabilities that are possible. And of course, there are possibilities beyond what you see in the video that can now emerge from simulation-based design and digital twinning. So for example, what you would see is that we can have not just one car, but we can have multiple cars. We can have data logging and automation pipelines within the simulation framework as well as within the development frameworks. We can have parallelization for, say, both training as well as validation of autonomy algorithms, where different cars are being put through different parameter sweeps. You can have human race AI, you can have an AI race AI, or you can have, even just for fun, human race a human, and actually use those data for calibrating your algorithms, for example. And you can have, as I said, parallelization, where you not only just replicate environments by brute force, but now have smart agent parallelization, where you can see that the vehicles are selectively perceiving, colliding, or interacting with their opponents based on the level at which they are being parallelized. And then just a few fun glimpses from one of our earlier research where we tried to do multi-agent reinforcement learning within this environment, and how the agents are competing is basically being shown as adrenaline rush movements, where you can see the vehicles taking each other over or blocking each other to make sure that the opponent is not winning, and those kind of strategies that or behaviors that emerge over the time from our training. But what's more important is not just keep things in simulation, but now be also able to transfer them to reality. And so we have shown with AutoDRIVE for several different vehicles as well as different tasks that you can now transfer your autonomy algorithms zero shot from simulation to reality. And this particular video also goes a step further to show how we can now also enable multi-agent algorithms to be transferred from simulation to reality, or even trained in the loop with real world vehicles, where you have a physical vehicle running state estimation algorithms to update its digital twin. And the digital twin can now interact with a virtual environment and a virtual peer vehicle to now close the loop with a multi-agent system. And that's the core idea and kind of potential that simulation and reality combined have to offer. So let us now talk particularly about the competition. So as Dr. Mangharam already highlighted, this is the 22nd F1TENTH Autonomous Grand Prix, which has two components. First is the conventional physical racing competition, which is happening at CDC in Milan. And as Dr. Mangharam highlighted, they are already underway with practice, and further phases of the competitions will be executed in the upcoming days. So the core idea of this physical competition was to have an in-person event at different conferences or locations all around the globe, wherein physical race cars and race tracks would be constructed, and time travel based qualification followed by a head-to-head racing format would be followed. So we wanted to kind of try to prototype and start generating the same design of competition within simulation so that it can be accessible to everyone across the globe without the restrictions for travel or other constraints. And so what we had started at IROS 2024 was to have a virtual competition that is held approximately a week ahead of the conference. So what this gives is an opportunity for the competitors to also participate in simulation, but physical races without the schedules conflicting or overlapping. And the idea behind this competition is that it would be completely virtual with simulated race cars and race tracks. And it would, for these initial deployments, follow a time attack racing format, wherein there would be a warm-up lap followed by 10 race laps, which would be quantified in terms of the racing metrics, as we will see. And then finally, a cool down lap, which would again be anything that the competitors choose to do. Some of them have tried out doing cool acrobatics just for fun. But yeah, that is the general format or idea behind the virtual competition. Another key point about the virtual competition was to have reproducibility and benchmarking through the data that's being generated. And so as a part of that, as well as to preserve the transparency of the competition, we have been providing the participants with the data of their runs. That includes ROS bags and other metadata, as well as videos and other material for their getting an insight into how the algorithms perform online while racing, and perhaps especially from moving from the qualification round to the competition round, they can actually choose to use those insights to now retune their algorithms for better performance and better performance versus safety trade-offs. So the virtual competition started somewhere around August, wherein we opened the registrations, and the competition kind of ended on December 9th, wherein we declared the final results. So we will be revisiting those moments again in today's presentation, and we will also be highlighting the competition results and the winners once again at the end of today's presentation. So in terms of the logistics, first of all, the competition followed 2 rounds. The first one was qualification, wherein we had released a sample track ahead of time, and this track was actually the digital twin of Porto track from one of the earlier F1TENTH physical competitions. And the teams were then allowed to, download these containerized or local instances of simulator as well as dev kit and get started with prototyping their algorithms. But the main idea here was to have minimum number of collisions. That was the only criteria to qualify for the competition round. And in the competition round, the idea again, of course, was to perform the best, wherein metrics like lap time, speed, and others were used to rank the teams on the leaderboard. In terms of the competition framework, as I mentioned, we had provided all the teams with a simulator container image, a dev kit container image, and local resources as well. So the overall idea for every participant here was to now just download these and get started with developing their algorithms that you can see as the small subsection within the dev kit container image. And then we also offered them different help in terms of distributed computing mode to speed up their computation. We also offered them GUI versus headless computing modes for faster execution with or without rendering options, and also kind of optimize the simulator and the dev kit along the way to service the demands that were now asking for more and to push the limits of their vehicles even further. So in terms of how we analyzed and evaluated the teams, here are the different race standards, metrics, and analysis protocols that we followed. So first of all, we had different race KPIs, which included things like the lap count and lap times. As you can see, we had all the teams visualized on live dashboards so that we can, first of all, judge the performance. We can see if there are any violations or any collisions and other penalties that must incur. And we also automated this in the backend so that we can automate the qualification or other metric logging, which may have human error if done manually. So in order to avoid all of that, we basically tied all these raw metrics to custom scripts that basically determine the qualification status or the race status, as you can see visualized live. And that helped us as evaluators as well as would help others in terms of benchmarking the autonomous racing software stacks that they are developing. So again, some of these metrics included things like the collision counts or the total and adjusted race time. Again, the total race time was something that we were just calculating, but the adjusted race time needed effort based on recomputation for any penalties that were incurred in real time. And then we also had other metrics for breaking tie, such as the best lap time or the maximum speed in a lap. Those were the race level key performance indicators. We also had several imposed for the vehicle level, which included things like pose, twist, and acceleration quantities. You can even see the live GG diagram of the vehicle just below the camera frame, which gives us an exact idea of what is the limit the vehicle is being pushed to. We also have other things like the wheel rotations, which kind of demonstrate the slips, and also the actuator feedbacks and sensor previews for LiDAR and camera, which give us a clear insight into how much the vehicle is being pushed to its limits and how exactly is it operating. There are teams who have used different sensing modalities. Some of them use LiDAR, some of them use camera, some of them use the wheel encoders, and some of them use the mix and match of these to now come up with robust algorithms to demonstrate high-speed autonomous racing. We even had a team at IROS where they could train their algorithm in simulation. This was the team from University of Kansas, and they could now zero-shot transfer them the trained algorithms onto their physical car when they also came and participated in the physical race at IROS. So finally, here is a glimpse of how the deployment looked like. This is a compilation from different teams. So what you see currently being visualized is phase 1, that is the qualification round. So this was the track that we had. It was pretty simplistic. And the main objective here was to not collide or collide a minimum number of times to qualify to the next round. But we had teams that were not too conservative, as you can see. The teams were already pushing their vehicles to the limits, but not too much so as to make sure that they qualify, but still fast enough to beat humans, definitely. Just for reference, when we drove manually on this track, we recorded a lap time of about 8 seconds. And the fastest team that put on the best lap time on this track was, I think, about 7 seconds. So that's a 1 second difference for even a human racing with, say, 25 years of, not 25, but say at least 10 years of gaming experience. And then this is the competition track, wherein the idea was to have a completely unseen track with higher complexity than the practice track. And this was to test the algorithm's robustness for adapting from one track to the other. And this track was released just a few days ahead of the final competition round. And the competitors had really a few, only I guess 1 or 2 days to fine tune their algorithms and make them work on the final racetrack. And this is what you see in action, where the vehicles are also not like, at least this vehicle is not caring about the track complexity. It's just driving to its limits. And again, similar to the qualification phase, we again had similar analysis of different metrics to rank the different teams on the leaderboard. So that resulted in these leaderboard rankings. So for the qualification round that has been depicted on the left side of the slide, we had 20 teams that successfully qualified. And amongst these, the top performers that we can see are 𝗏𝗏 from Level University, Austrian Kingdom team, and Solo Driver. So these teams performed really well in the qualification round, and all of these teams that have successfully qualified subsequently went ahead and competed in the qualification round, wherein the tables turned a little bit. We had teams shift up and down in the competition. This is where we see that the top performance in qualification were also the top performers in the competition round. That is Team 𝗏𝗏. And we had a few switches between rankings. So in the ultimate competition, Baby Driver secured the 2nd position, and we had Team 𝗏𝗏𝗏𝗏 ramp up their position to secure a 3rd place ultimately. It's also worth noticing that the time difference between these teams, especially the top performers and the center order performance, is really, really close, except for the first team who has like crazy times put on the leaderboard. Most of the other teams are really close in terms of their lap completion times, and it just comes up to a fraction of a second across, say, 10 laps that we were measuring the time for, as well as the collision counts to now decide who takes which position on the leaderboard. So once again, congratulations to all the winners, and even congratulations and huge round of applause for all the participants who qualified and competed in the final rounds, to have put all the effort and realize their algorithms come to life in simulation. So with that, we conclude our part of the presentation and ask the teams who are here to be ready for their presentations. The first team couldn't be here, that is the team 𝗏𝗏, and they have passed on a pre-recorded video of their presentation, which we will play, following which we will ask Mason to quickly talk about their strategies that they have employed for securing a winning position in this competition. Before I play the video, or while I play it, can someone please confirm if the video sound is audible on Zoom?
Yes, we can hear you. Yeah, go ahead.
Perfect.
The video's audio is not coming.
Oh, okay. Let me-
Yeah, from the Hey, everyone, I'm William.
Hey everyone, I'm William from the Vol team,
Yeah,
and I'll be
go ahead.
presenting to you today the strategy that the Vol team had for the F110 CDC competition. So first of all, a quick word from the Vol. So we're student clubs from the Université Laval, and we're composed mostly of undergrad students. So we've been competing in the F110 since 𝗖𝗲𝗴𝗂𝗏 2023, but this is our first participation to a virtual F110 race. So basically, we had all our race stack for the real vehicle, and we migrated it to 𝗔𝗴𝗲𝗶𝗂𝗏 to run on the simulator for this competition. So our race strategy usually revolves around deployment speed. So the more you can test, the faster you can go. So it's not always about just working on algorithms, it's about working on the workflow. So how can we deploy faster on our robot? How can we test race lines faster? How can we deploy different algorithms faster? Because at the end of the day, the tuning that we do is not something that it's something that takes a lot of time. So we have to test a lot. So we have both reactive and map-based algorithms, and the main algorithms that we use are listed below. So the 𝗏𝗏𝗏𝗏 algorithm, which is map-based, the map controller, also map-based, the disparity extender, which is reactive, and the Stanley controller. For this competition, we did the qualification with the disparity extender, but the real race was done with the 𝗏𝗏𝗏𝗏 algorithms. So I'll just play it here so we can see our rust bag on the side, so we can see the LiDAR scan in red, the current localization in purple, and the race line in green. So we achieved a best lap time of 10:35 without crash, but we were able to get some lap time of 9.7 seconds, but there were some times where the vehicle would crash, so we went for the safer option with this race stack. So I'll go into a bit of more details into what our map-based stack does, because it's a bit more interesting than the reactive algorithms. So basically, in the sensor side, we use the wheel encoders to do a wheel odometry node. So just a simple odometry node based on the technical sheets that's with the competition website. And then we also took advantage of the IMU data and fused it with the wheel odometry using an extended Kalman filter. So we used the one from Rust2 robot localization and used basically the default setting, if I'm not mistaken. And it gave some pretty good result that we then feed into our GPU accelerated particle filter. So we use the particle filter from that's with the F110, and we forked it, and it's basically the same thing, but and we run it on the GPU in the Rust2 𝗏𝗏𝗏𝗏. And we had to jump into some hoops to make it work with GPU on Docker, but we did it, and it's available on our GitHub. And after that, the pose from the particle filter is sent directly to the control algorithm. So in this case, it was the 𝗏𝗏 node. And the raceline is computed completely offline. So we have a raceline generation repo. So the one from 𝗟𝗲𝗴𝗂𝗲, the global race trajectory optimization that we tuned. And we tuned the min time race algorithm that you saw on the last slide. And the 𝗏𝗏 algorithm then looks ahead of the vehicle, finds the waypoint that's at a certain look ahead distance, and then steer or throttle according to the model that we put for the car. So we also tried the disparity extender on the competition the map layout, but it was kind of getting stuck into some corners. There was a lot of tight turns, and we weren't able to do it with the disparity extender, so we had to go for the map-based stack. After the competition, we will open source some of our algorithms. So the disparity extenders, we will open source it. The container workflow that we use, so we have a setup of Docker Compose and a bunch of things that we are gonna open source too. And we also have a raceline editor and optimizer, basically a graphical user interface that we use to deploy our racelines faster. And we will release it next year, I think, probably after 𝗥𝗏𝗴𝗂𝗏 or something like that. So keep an eye out on our GitHub, and I hope that I'll see you on the next virtual race. Here are our socials, and I hope you learned from something from this presentation. Thank you. Hey everyone, I'm Will.
Yeah, so that was the presentation from the first place winners. Mason, if you are ready. Mason is the member of baby driver team, and they ended up securing the second place.
Hello, you guys hear me?
Yes, we can.
Okay, yeah, I'll just give a kind of quick overview of what I did. By the way, my name's Mason. I studied at the University of Virginia, computer engineering and stuff. So anyway, here's a quick overview of the autonomous racing stack I was using. For the odometry, it was sensor fusion between the IMU and the throttle sensor. I'll talk a little bit more about that in the next slide. For localization, I was just using the ROS2 package, the adaptive Monte Carlo simulation package. For the lateral controller, I was using Stanley's method. And for the speed controller, it was just a lookup table between the steady state speed that the car is usually going to be at with that throttle, kind of just backwards figuring out what the throttle is to get to a certain speed. Really just aiming for something like super simple for the first time submitting something like this. It is a map-based algorithm where you kind of generate a racing line and then using some localization and control mechanisms to follow that race line. For the odometry, I started off using just the integration of the acceleration to figure out what the velocity was going to be. That ended up having issues where it kind of drift over time due to like errors in acceleration, or if you like crash and hit a wall, then your whole integral would be kind of messed up. So I kind of fused it with some type of steady state signals. Using that same basically lookup table, you could kind of figure out that if the throttle's at a certain percentage, the simulation should at some point kind of reach that steady state speed. So the idea is to kind of fuse between some type of like velocity that you get from integrating acceleration and kind of what you expect the car to be at steady state speeds. And you kind of fuse between them dynamically using your kind of alpha looked up between acceleration. So for really low accelerations, when you're basically at zero, you're expected you're kind of at steady state speeds. So you kind of do that purely. You kind of basically filter up to that. But then when you're doing more dynamic maneuvers and your acceleration is greater than a certain amount, you're purely relying on the speed from acceleration readings. And this did okay. I mean, there's obviously some things you could do better, but yeah, this ended up working out okay. Yeah, and then this is the raceland I created. I used the same TUMS package that the other team was using for global race trajectory optimization. Create some script to kind of export a track line from this, and then import it there. I chose for the minimum curvature method of raceline, which ended up being okay for this. There's some things to improve upon where definitely some weird behavior, but overall ended up doing all right for this competition, and but some things to definitely improve on there. But yeah, that's kind of like a brief overview of what I did. Yeah.
Thanks a lot, Mason. And once again, congratulations to all the winners for putting up a terrific performance on the virtual racetrack. We now hand it back to Dr. Krovi and Dr. Mangharam for final thoughts. Thanks.
Thanks a lot, Chinmay, Tanmay, and congratulations once again to the winners. Big hand to you. I know it's a virtual race, but we are all very excited about this competition. And I just want to have Professor Venkat Krovi give the closing session. Yes.
Oh, I think this was an exciting perspective in terms of outlining what the possibilities are for expanding the competition. We've gone through sort of 2 sets of trials here, first at IRAS and now at CDC. But Dr. Mangharam and I have been talking about engaging the community with both expanding the scope of this with larger scaled vehicles and with increasing the complexity both in the physical and the simulation need. So just to give you a perspective of the types of things that are possible, one could imagine the racetrack now being customized to include not only geometric complexity, but also traction complexity, including, so the sky is the limit in terms of how one could stress test these autonomy algorithms. And I think stay tuned for exciting new competitions to come. So maybe Dr. Mangharam would like to add to this, and RoboRacer, and yeah. You're muted.
Yeah, thank you so much, Venkat. I think that there's as F1TENTH in 2025 will expand to RoboRacer.ai. And as Venkat mentioned, it will go to multi-friction tracks. We will also have a community session in January called the State of the Race to give feedback to the community, get feedback from the community and to outline, what is the roadmap for the next 2 years for RoboRacer. And then, as he mentioned, the sky's the limit. It's like, multi-friction race tracks, non-planar racing, and then eventually we wanted to look at off-road racing. Essentially, this, first of all, pushes the pipeline to go from a very modular perception planning control rule-based system that we have today to a much more end-to-end and learning-based system. And that also allows a lot of the research that many of the F1TENTH and RoboRacer community members are doing to feed into a more modern learning-based and a differentiable stack pipeline for racing. And this will also scale to platforms that are not just 1/10, but smaller and much larger to have competitions at different levels. So that brings us to the close of this session. A big thank you to Chinmay and Tanmay for putting in hundreds of thousands of hours in getting AutoDRIVE to be such a flawless and scalable system, allowing the community to really participate in this competition. I think it's really commendable that, students themselves are building a lot of the platform, and now we are able to enjoy the benefits of that. And we look forward to a very exciting 2025. Before that, we have our December race at CDC, and stay tuned for those results. So any final notes from the audience or anyone else? Yes, go ahead.
Could you indicate the Twitch?
Yes,
It's
yes.
on Twitch.
The Twitch link has been posted on LinkedIn and also on the F1TENTH channel. And I think if someone wants to post it in the chat here, please go ahead. And so this is live streamed on Twitch, and the videos are offline now because the competition trials are offline after 6 p.m. here. But tomorrow you will see there are multiple cameras giving you multiple perspectives, and the final competition will be on Thursday. So join the Twitch channel tomorrow during the daytime hours in Europe. All right, folks, thank you. And once again, a big congratulations to both the winners of the competition and the students facilitating this competition. Thank you very much. Yeah. And before I end, I need to also thank Martina. She has been a big source of inspiration and help here.
I would just like to say, on behalf of the CDC organizers, thank you very much for organizing the simulation race and the physical race. We are all very excited to see the development that is happening in the field. And I started with the first, the first time I remember going to CPS week and hearing for the first time about the F1TENTH being designed and built. And now it's incredible what you have managed to build in the last 5 years. So thank you very much.
Cool. Thank you so much, Martina, for your support here. And that ends our session today. Please stay tuned on our Slack for new and exciting news coming up next year. Goodbye.